Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using Knime. This new section begins on dimensional reduction, and it's going to deal with getting smaller data sets. And this section is beginning with missing values in more detail than we've covered before. Now, before we get into this chapter on dimensional reduction, I wanted to take a minute and point out to you where I got some of my example datas and workflows. In the original version of my class, I had written all my own sample routines. But as I re-recorded these new versions of these videos, I was off at the Knime hub, and there was some incredible work done by two people you see here on the screen, Marie Wyndham, who's a data scientist at Knime, and Rosario Silipio, I hope I'm pronouncing her name properly, who's both an expert in data mining, and she's also written a number of Knime books, the Knime cookbook and so on, just an absolute expert on Knime as well. And they wrote some very advanced routines that took a lot more into account than my simple sample techniques. So what I've done is I've taken their examples from the Knime hub and I've just extracted just portions of it for each section of the dimensional reduction class. If you want to go out and see the full version of their workflow, because what they've done is an incredible job on the Knime hub, where they show you literally how to compare all of these dimensional flows one against the other. And it's very worth reading. They do a really good job of explaining it, and they give you a much more elaborate workflow than my samples do. Now, recently we've seen very large increases in the size of the data sets that we're being asked to do data analysis, and more particularly the number of attributes in that data set, which we call features. And it's triggered the development of both big data platforms and parallel data analytic algorithms. But at the same time, though, it has had to push people like ourselves to use dimensional reduction procedures. And dimensional reduction is dealing with the idea of removing columns from our data set, features from our data set that don't serve value. They don't provide meaningful information that improves the quality of the model. So dimensional reduction is not only useful to speed up execution time, but it actually can make the model more accurate as well, because we're removing noise from our input, basically that might cause faulty results. And in fact, just the example I'm going to show on missing values will show you how different values can improve the actual return of the predictive model that you're building. In the data mining section, you're going to see there's many algorithms that I'm going to be teaching you, from decision trees, naive Bayes, neural networks, logistic regression, random forests, and more. And most of them, though, due to their heavy internal learning algorithms, they find it very difficult to deal with large number of columns. This is something that's inherent to the way the algorithms are designed. That the problem is not the size of the data set in terms of the number of rows. The problem is the size of the number of columns it's having to process. And many of these algorithms have to loop around these input columns. So the more columns there are, the more slowly they run. Now, the corollary to what I'm discussing here is that one of the key principles in data preparation is to do as little damage as possible to the natural structure in a data set. So we need to keep that in mind. Now, this is a summary, a repeat of the slide we just did when we were talking about transformation. Why is data missing? Well, it's not contextually accurate or appropriate to us, and we call that do not care conditions. Or lost data, that it was either mistakenly erased, or somebody refused to answer a question, or it was simply not entered correctly, and so on. A critical differentiation is between missing values and empty values. When a value is missing, it exists, but it's not recorded. Let's say a customer's weight. I don't know how much the customer weighs, but they do have a weight. And an empty value is one in which no real world value can be supposed.
For example, what is your spouse's name? You don't have a spouse, then your spouse doesn't have a name. That's the difference between missing and empty. Now, handling missing values we talked about in the transformation section as well. We can replace them with substitutes like the mean, median, mode, or we can take the closest fit based on some algorithm, or we can just do parallel methods where we handle these missing values through the mining process. So in other words, we might say just don't consider rows with missing values. That falls into the do not care category. The most straightforward way to handle them is simply to count the missing values, and when you hit a threshold that's too high, then there's so many missing values that column can't be counted on to be used in your model. The question that should naturally come from that is, what is that threshold? You might say if 5 to 10% of the values are missing, then I can't use it, or more than, well, we don't want to guess. And thankfully, we can do this in Knime. We can actually automate the process of figuring out what is the best value for missing value threshold. The concept I'm going to show you is very straightforward, and we're going to walk through it in Knime, but the process, it would be similar in other tools. Count the number of missing values in all the columns of your data set. Then compute the ratio of missing columns to the number of total rows. Remove the columns of your data set where the ratio exceeds the threshold. And the trick is computing that threshold. What is the optimum threshold? And that's what I'm going to use Knime for. So let's go ahead and put together a Knime example that tries various thresholds and loops through them all, attempting to find the optimum value.
All right, so for an example, what I'm going to do here is I've extracted some code out of one of the Knime examples where they show data reduction, and they do a whole comparison of each of the mechanisms for dimension reduction. So what I've done here is I've got a sample CSV reader, and I've just generated a target variable, yes, no. This is all I'm trying to predict here. And then all of the variables are just, some are integers, some are strings, doubles, and so on. It's all just generated data, 230 columns. And I'm partitioning it into two parts. One, and this is a part we're going to cover in another chapter when we start covering data mining. So for now, just bear with me and understand that partitioning is about taking the data set and dividing it up. So I'm putting 70% of the file relative and drawn randomly is going to become the training data set, and 30% is going to become the test. And I may as well fix that little comment there so it actually reads accurate. Now what I'm going to do here is I'm going to loop through all of the possible missing value column filters. When we look at this column filter parameter, we specify the threshold to say if this percentage is missing, that column will be filtered away. And I'm going to use a flow variable called the new parameter, which is being passed out of here. So I will filter the output of this. You can see I still have 50,000 rows, but I only have 67 columns. I began with 231 columns. So the filtering away, but as we said, what is that threshold? That's what this module, this meta node, is all about. So let's take a look at what's going on inside of here. I'm doing a parameter optimization loop. That's the loop start right here and the loop end. In the start, I've created this value called new parameter, and it's going to start with 0%, and it's going to go up through 90%, and it's going to go up by increments of 10. So we're going to try 0, 10, 20, etc. through 90. Now, I'm removing the target column because it can't be filtered away no matter what happens. So I've simply split this and said the target column is going to get dropped. All of is going to go into the, and all of the rest of these are going to go into a separate. So you can see 230 columns go here, one column comes here. Now, the missing column filter here, we're going to start by looking at that, and says it's controlled by the variable again. So the new parameter variable is controlling how this is configured. So the first time through is 0%, 10, 20, 30, and so on. So I filter the columns, and I've still got, after filtering it, I only have 76, which means about 200 and, 150 of them or so were nulls, all nulls, and so they were filtered away. Now I take for the rest of the missing values for them in the data set. Integers I use the mean, doubles I use the mean, and for strings I use a fixed value of unknown. That's how I handle all the missing values. There will be no missing values in my data set. Now I concatenate the target back onto this field. So now I've got all the data back again, 77 columns and 35,000 rows. Now, equal size sampling is going to remove rows from the input data set such that the values in a categorical column are equally distributed. So what I want to do is say I want the column called target to be equally distributed so that I have the principal same number of values. So I've dropped down to 5,064 rows and 76 columns. Now, we have not introduced the whole concept here of doing data mining yet. So for now, I'm going to ask you to just ignore this module and simply accept that this is what it does. It's performing 4 different categorization functions. It's naive Bayes. Each one of these functions, a neural network when the columns are all numeric, and a naive Bayes. And you know what? I can show you the function. It's performing a naive Bayes and a decision tree. So I'm going to do a neural network, a naive Bayes, and a decision tree. And I'm going to combine all of those, and then I'm going to find out which one, based on the data it had, came up with the most predictive model. And I'm going to score that prediction, or keep that prediction score. So the output of this is actually going to be the accuracy for the naive Bayes and the accuracy for the decision tree, and there is no accuracy for in this case, the neural network, because it was not all numeric columns. So I can see what the accuracy was in this particular example. Now, the last thing I have to do as part of my prediction is to apply those models against the real data. So remember, we had 35,000 rows came in as our test training data, and then the testing data is 15,000 rows. Well, all 231 columns came in. I need to filter those columns that were removed. So I'm using this model for the missing value handler. I'm taking that same model and passing it in, and I'm taking all of the columns here, and we will look at this, and I'm using a reference column filter to remove all of the columns from the test data set if they weren't in the training data set, if they were removed. And then I fill the missing values just as I did with the training data set, using the same model. So finally, the output of this, when I look at the actual set of parameters at the end of the loop, all of the parameters it tells me was at 0, I was at 46% accuracy. And then it got up to just under 57%, and then 59.3 and 58.4. So you can look at this and say it seems to be at the 20% rate that I can get a 59.593. And I'll look at that just to be sure I was reading that correctly under best parameters, and 0.593 at 20%. So my classification model now with my missing column filter. The new parameter value that I'm going to use right there is going to be 20%. So the value that came back here, let's just look at it. The new parameter is 20, and I convert that to a variable called new parameter, which is set at 20. And then in the flow variables, I set the new parameter value as the missing value percentage. This is how we automate computing the best value to use for missing values. Again, I know the critical part here you haven't seen yet is this bag of models and predictive optimization. We're going to get to that. We're 4 or 5 chapters away, and then we're going to cover this. So for now, just sit tight and understand that we're using a concept of a loop, and we're trying lots of different models to see what threshold is going to work best for us.
That completes this chapter of the class. Feel free to move on to the next chapter.